Thank you, Lisa. Thank you, Wuji, for organizing the CEDA seminar. My name is Zhipu, and thank you everyone for joining our virtual meeting today. Today, I'm going to talk about the endogenous representation of asset returns, a new perspective for the modeling and estimations. So this is a collaborated work with Professors Alex Skolnick and Sang-Yun Oh from the Department of Statistics and Applied Probabilities at University of California, Santa Barbara. I want to thank Professor Alex Skolnick and Sang-Yun Oh for all the guidance and provide this seminar opportunity to me. Without each of them, this work would be definitely impossible. So first, let's look at the background of our research. So the background of our research is that in the finance area, how to model the asset returns has been one of the central issues for decades. As we all know, in 1950, Harry Markowitz introduced the modern portfolio theory. In 1964, on the framework of the modern portfolio theory, William Sharpe introduced the capital asset pricing model. This model theoretically determines the appropriate required rate of return for an asset, and it implies the one-factor model, and the asset return is modeled as the market return multiplied by the beta plus a specific return. As an alternative, in 1976, Stephen Rose proposed the arbitrage pricing theory, which relies on the asymptotic arbitrage argument, and it allows for the multiple risk factors in a factor model for the asset returns. So since then, the factor models have become very pervasive in both the theoretical literatures as well as in the investment practice. And many other factor models have been proposed, including the pharma fringe models, the PCA factor models, the macroeconomic factor models, and so on. So generally, factor models for equities is expressed as y equal to bx plus z, where b is the factor loading matrix and x is the factor. So there are different types of factors. We can have the market factors, such as the S&P 500 index or the MSCI world indices. We can have fundamental factors, such as the value, growth, the return of equity, and we can have the macroeconomic factors, such as the interest rate and unemployment rate. And finally, we can have statistical factors coming from the principal component analysis, PCA. So what is a factor? How should we understand the factor? So we can refer to this statement and think about factors as the Adam Smith's invisible hand. This statement comes from the Lazard Asset Management, and it says, we define a factor as a source of common exposure or a characteristic that is shared by a group of securities that helps explain their risk and return behavior, both individually and collectively. So we liken factors to many invisible hands at work in the market and portfolios. So here is an example for the factor model using the statistical factors coming from the PCA. Suppose we gather the P by N data matrix Y, where P is the number of assets and N is the number of observations. We can compute the P by P sample variance matrix S, and we can extract the first factor by maximizing the explained variance, which is given by these optimization problems. So here the factor whose variance is S squared and its corresponding factor loading B, which is the optimizer of this problem, is empirically market-like, meaning that empirically this factor is interpreted as a market factor, and its factor loading is interpreted as the market beta. Empirically, most factor loadings, most factor loadings in the B are positive. And this is consistent with the fact that when the market goes up, generally most of the asset prices will go up. And if the market goes down, most of the asset prices will go down as well. So in the statistical factor model, if the top 5 principal components are selected as the statistical factors, and the principal components are estimated from the historical returns of the component stocks of the S&P 500 index, then here's a plot for the out-of-sample explained variance by the statistical factor model. And in this case study, the explained variance is measured by the R squared. So the x-axis in this plot is the chosen time horizons in our case studies, ranges from the year 2000 to 2018. And during the time horizon, the PCA factor model is recalibrated every 3 months. And from this plot, we can see that despite the S&P 500 index contains almost 500 component stocks, the 5 statistical factors can explain about 40% of the out-of-sample variance of all the asset returns for the past 20 years. Okay, so what is the motivation of our research? What can we do about the factor model? So our work is motivated by the factor modeling. And as we all know, in the equity factor model, if we denote P as the number of assets, K is the number of factors, and N is the number of observations, then we can express Y equal to BX plus Z. This is generally being used for the model's estimation, right? So in the factor model, the universal assumption is that the covariance between X and Z is 0, meaning that elements in Z is uncorrelated with the factors in X. And we use this assumption to estimate some parameters in the factor model. But which variable is the model parameter depends on the type of factor model we use. So for example, here, in the fundamental factor model, the factor exposure B is generally prescribed, predetermined, and the estimate is the factor return, the matrix X. Well, in the macroeconomic factor model, the factor return X is generally prescribed, predetermined, and the estimate is the factor exposure. Well, in the PCA factor model, because of the identifiability issues, generally the factor exposure and the factor returns are partially estimated together. And this may lead to some difficulties in the interpretation, in the model interpretation. So from the model estimation perspective, factors are often regarded as exogenous. That is to say, factors are regarded as representations of common exposures or characteristics that are shared by all assets or group of assets. Right? So what is a good asset return model? We believe that a good asset return model should be able to achieve 2 goals. Number 1, it should be able to explain the risk, or it can be able to explain the variance of the asset returns. And number 2, it should be able to explain the behavior of the asset returns, either individually or collectively. Factor models are able to decompose the risk of an asset return, and factors are interpreted as the invisible hand that drives the major movement of the asset returns. So factor models definitely belong to a good asset return model. But the question is, are the factor models the only way to achieve this? Is there any other type of model that can model the asset returns as well? So to answer these questions, we start our work by looking at the spatial interaction model, which is proposed by Cole and other authors in 2011. Basically, the spatial interaction models describe the asset return Y as the traditional factor model plus a spatial interaction term, rho times W times Y, where here W is a P by P matrix and is exogenously given. It uses the quantities related to the locations of assets, such as the geographical distance of the equity exchange centers where the assets are traded. So for example, here, the spatial interaction models can be applied to model the returns of Eurozone stock indices. So here in the plot, we show 11 Eurozone stock indices coming from Austria, Belgium, Finland, and so on. And the elements in the spatial interaction term, the W matrix, represents the driving distance between the capital cities of between two countries. And Cole's paper showed that the spatial interaction terms actually is statistically significant to capture the asset returns in addition to the traditional factors. So this spatial interaction model is significant to explain the asset returns for the Eurozone stock indices. But we have empirically demonstrated that this model is not applicable to United States equities. We find out that the spatial interaction is not significant at all in terms of explaining the asset returns when we use the S&P 500 component stocks, for example. So this type of model for United States equities, this type of model is actually still a factor model. So is there any other factor model? Is there any other type of model that can model asset returns besides factor models?
Can I ask a question about that? So yes. in the Europe model you described, you looked at distance between capital cities of the countries where the stocks were located. In the US, of course, there's only one capital city, so the distances are all zero. Is that what you mean when you say it's inapplicable, or did you look at, for example, this distance between the cities where the head offices of the companies are located? Or in other words, I'm wondering whether it's inapplicable basically by definition, or whether there's actually something empirically you tested and found that it didn't explain much.
Yeah, thank you for asking this question. So based on the Cole's paper, how to define the quantities measuring the location of the assets, it kind of depends on the users. In the Eurozone stock indices case, because most of the stocks are traded in the exchange center, and the exchange centers are generally located in the capital cities of their country. So it's not surprising that they are using the capital city as the location of the asset. But when back to the United States equities, we have only one capital city, so capital city definitely is not a good choice. In our case studies, we use the location of headquarters of the companies issuing the equities. We use such a definition to define the matrix W, and still we find out that such a matrix W does not play a significant role in explaining the asset returns.
Thanks.
Yeah. Okay. So so the question is, besides the factor models, can we propose any other type of model that can model asset returns? To make this, to take this question to its ultimate conclusion, we are thinking about if it is possible to build a model without any exogenous factors, but it can still decompose the asset returns as endogenously explained return plus some residual. So we propose the model as y equal to ay plus z, where A here is a sparse matrix, it's a p by p matrix, and it's an interaction matrix. Because such a proposed model is related to a graphical model in the literature, and because of that, we call this model as the graphical representation model, or short for GRM model. And that is the model we propose in this work. And back to the question we just raised, we can offer our answer. Yes, factor models are not the only model for asset returns. The graphical representation model can work as an alternative. So here in the plot, we can see that when model the returns of the S&P 500 component stocks, both the PCA factor model and the graphical representation model explain very similar proportional variance in the asset returns for the past 20 years. Despite that, both curves fluctuate a lot as time goes by. Both curves move in pretty much a synchronous way, right? So what is a graphical representation model? What are its desirable properties compared to the factor modeling? And how to estimate the model's parameters? These may be the questions we have in mind right now. So let's move on to the next section, the theory part of the model. So suppose.
Sorry, but just a quick question before you move on to the estimation part, which I'm sure you've figured it out and all that. But are you basically saying that to predict returns, you use its own returns, basically?
You mean this plot?
If you go back to your previous slide. Let's can I think of this in a very naive way. So if I want to explain IBM's stock return, right?
Mm-hmm.
Say traditionally we would use a factor model, like value size and all that kind of stuff to explain it, or PCA if you want. But here, if I want to explain just IBM's return, literally, you're saying that IBM explains itself. Yes?
No. The matrix A here actually has a one property, that is all the diagonal elements are 0, meaning that we won't put the response variable as one of the predictors. For each yi, we use all the remaining y as a predictor to explain y.
Oh, I see. Okay.
Yeah.
Okay.
That's a very good question. Thank you.
Okay.
So is it true that like in a CAP-M type model or a market type model, when you put in your factor as the market to explain security return, since if the security is part of the market, you're doing kind of what Raymond said, at least a little bit, right? You're using in part the security return to explain itself.
Mm-hmm.
Is that right or wrong?
For the CAP-M one factor model, it is right because in the CAP-M equations, y is explained as in terms of beta times x, right? And x is pretty much people estimate x by equity indices, which is basically a linear combination of all the assets in the indices or in the market. So in the CAP-M one factor model, pretty much the yi is explained partially by itself. So here, what we propose is kind of different from the CAP-M one factor model. Here we won't use yi in the predictors when we explain yi.
Can you say a little bit more about the motivation for this formulation? So, I mean, is there an economic motivation, or is this a type of relationship that people have studied in other data analytics problems that's proven to be useful, or why this as opposed to something else?
Yeah, I think our motivation is that first, when we look at the CAP-M one factor model, we realize that the portfolio return X is estimated by equity indices. And equity indices actually is a linear combination of all the assets. So we are thinking about if it is possible to use, it's possible to explain assets endogenously, meaning that we use all the remaining assets returned to explain one particular asset. And besides that, when we look at the spatial interaction model, what Cole proposed here, W is a driving distance, and we have empirically demonstrated that W, when we use the US equities, W does not work, and it's very hard to determine what would be the best location for assets for United States equities, right? So we are thinking about, can we propose something that is similar to W, but it's not matched by the distance, right? So motivated by these two, we are thinking about whether we can model Y as A, Y plus Z. That's pretty much the initial motivation of our work.
So are you saying then that the sparseness is a measure of conceptual distance? The entries of A are non-zero when two assets are close to each other, and 0 when they're far away from each other. Is that the connection with the spatial model?
No, A here, we don't know. We don't know what are the elements in A. We don't know whether it is a distance or what is something else. We don't know right now, right? For the spatial interaction, W is measured by the distance, but here A is not necessarily a distance. It may be.
Oh, no, when I say close, I mean, the spatial model says that assets that are geographically close will tend to covary. And abstracting from that, if A is to be sparse, then many entries are going to be 0. That's what it means to be sparse.
Right.
And can we think about that in a motivational or intuitive sense, following up on Bob's comments, by thinking that is analogous to, in the spatial model, two assets being very far apart?
Yep.
Okay.
We can make that analogy. But here for the matrix A, we didn't know that what is inside it. What is inside A?
Can I just quickly follow up with a quick comment?
Viscosity.
Sorry, I just want to follow up with a quick comment. I think the difference is that A is going to be estimated here, whereas in Ku's model, the A is prescribed.
Right. Right.
I'm sorry, it will be estimated, but it will actually still be all 0 when it's actually that specific asset, or estimated like the whole matrix.
So we will talk about how to estimate A in the following section, but I can say that here A will be estimated based on all the historical returns of all the assets involved in the model. Okay. Any other questions? Okay, so let's move on. The theory part. So let's denote Y as the returns to P asset, where Y is P-dimensional random vectors. And without loss of generality, let's assume that Y is mean 0. Then for any P by P matrix A, we can define the residual vector Z as Y minus AY. So if the ith row of the matrix A contains the coefficients Aij, then for the ith asset, we have that the residual Zi is equal to Yi minus the sum of Aij times Yj for all j not equal to I, right? And these equations expressed in terms of I equal to 1, 2 up to P. So in order to find out all the coefficients Aij, one can propose to minimize the residual Zi in the least square sense, which is equivalent to solving the P number of linear equations of this optimization form. And this is the optimization problem. And the solutions are rows of the matrix A, which has a 0 diagonal. So we provide this theorem, which is saying, suppose Y is a P-dimensional random vector having 0 mean and positive definite covariance matrix sigma, such that omega matrix is this. Here, omega is the precision matrix defined as the inverse of the covariance matrix. Then there exists a unique minimizer A, such that in the system of linear equations, the residual terms are minimized as expressed in the equation number 1 here. And the minimizer A is equal to identity matrix minus D times omega, where D is the inverse of a diagonal matrix of omega. And in particular, we can express the elements of A in this form in the equation 2. So,
right, I've got a question about that. Can you go back to the last slide? So you're assuming that the covariance matrix is invertible. So if I'm not confused, I think that means you have more, at least as many observation days as you do stocks. Is that right? Because otherwise the rank of the covariance matrix is at most the minimum of the number of observations and the number of stocks. Am I
Yeah.
confused on that, Alex, or?
So here right now, we are still talking about the theory part, right? Here, sigma and omega are the true sigma and omega for the random vector y, right? We haven't collected any observation yet.
Okay, they're the true population.
Yeah, they are the true covariance matrix and the precision matrix.
Okay, so that is that question, but then I think I've got another one. So, so I'm happy with the assumption that sigma is invertible, but on the other hand, I suspect that some of the eigenvalues are quite small, which then suggests there may be matrix conditioning issues that arise here.
So I think that when we collect the number of observation which is small relative to the number of assets, it is possible that the estimated covariance matrix has very small eigenvalues, which may lead to some problems when we take the inverse. But in that case, as we can see later on in the estimation section, we introduce sparsity regularization that helps to estimate a robust estimator for omega and for sigma, and that helps to resolve this issue.
Okay.
Okay, any other questions? Okay, if you have any questions, please feel free to ask. So let's move on. So under the result of the theorem, we can decompose the return y as ay plus z, while the term ay is interpreted as the endogenous return, because this is the return that is explained by other assets return. And the matrix A actually encodes the interactions or the interaction between the stock issuers, between the firms that are issuing the equities. And we can see that the covariance under the theorem, the covariance of yi and zj is 0 for any I not equal to j. That simply means that in the expression here, zi actually is uncorrelated with each of the predictors in yj. Okay. And finally, we conclude that the covariance between zi and zj can be non-zero in general. Okay. So based on that, we can also have the variance decomposition. The true sigma implied by the theorem can be expressed in terms of A and omega. So sigma can be expressed in terms of A sigma A transpose plus this quantity. Where we define the first quantity, A sigma A transpose, is the endogenously explained variance. And the second quantity is the remaining variance. The variance of Z expressed in terms of D omega D, and this is not equal to the second quantity. And in the expression omega, as we said, omega is a precision matrix, and also it is known as the concentration matrix. And this is the core quantity for the model estimation as well. So we have the decompositional variance proposition. So if the precision matrix omega of the random vector y is positive definite, that is to say the diagonal elements in omegas are positive, then if we define A in the theorem, then the variance of yi, the i's asset return, denoted as sigma I, can be decomposed into this way. Well, variance ay ii is the endogenous variance of yi, and 1 over omega I is the variance of the residue. And in addition to that, we can decompose the covariance between yi and yj for I not equal to j, denoted as sigma ij. And we have the decomposition form in equation 4. So here, the endogenous variance simply means that the variance of Y that is explained by all the other assets in the system, in the financial market. And the residual variance is the variance that is specific to YI that cannot be explained by the system. So here's a very simple example. Suppose we have only two assets, and the two assets have correlation rho ranged from -1 to +1. So we can express its sigma, the covariance matrix, as this form, and under the theorem, we have the matrix A expressed in this way. So the endogenous variance can be computed as rho squared times sigma. So when rho is 0, then the endogenous variance is 0. And when rho is close to 1, all variance may be explained endogenously.
Could you just remind me of the definition of script sub y, script E sub y?
Script YA is defined as the variance of AY, which is the variance of the.
Okay, so that's a definition, not an equation. Is that right?
So variance of AY equal to this quantity. This is the equation, and we denote the variance of AY as script EY of A.
Okay, so you might want to use 3 bars instead of just 2, an equality there. Okay, thank you.
Yeah. So likewise, the variance of the residual Z can be given in these quantities. And from this quantity, we can see that when rho equal to 0, then all the variance is explained by the residuals. And when rho is 1, the residue is 0. So
excuse me, I'm just, if you can go back to the previous example, right? So sticking on with just the 2 asset example. So I sort of get your motivation starting with the location model, but it just seems to me that you're trying really hard to not use the most obvious endogenous regressor here, which is the stock itself, if you're going this way. Is it not?
So in this case, we have 2 assets, and we can see that in matrix A, right? Matrix A, the diagonal elements are 0.
No, I know, but that's by design, right? But if you want to explain with, say, 2 assets, what is this the best predictor of 2 assets using the assets itself? It's sort of very obvious that it's the asset itself.
So this is a very simple example. It assumes that in the financial market, we only have 2 assets to trade.
No, I know, I understand that, but I'm just trying to understand why are we? Is this study like driven by some economic motivation, where you're trying to say there's some sort of economic thing that you can show using this model, or is it purely a statistical exercise?
So this work, we motivated by the spatial interaction models, and that's how we propose the AY terms here. And
but then the spatial model is also more or less like a statistical thing, right? In some sense.
Well, so we motivated by spatial interaction model, but actually we do not go further for the spatial interaction models. This spatial interaction model is only a motivation, but we do not go deeper for that direction. We motivated by that form, but we
put it this way. If there are only 2 stocks, IBM and Cisco, yeah, and you ask anybody off the street, what's the best explanatory variable for IBM? So most likely they would say it's IBM itself and not Cisco.
Yeah, so in this case, we only have 2 assets, IBM and Cisco. Then if we hope to explain the return for the Cisco, then the only asset we can take as a predictor is the IBM.
But then the next question is statistically why and also economically why?
Because here we only have 2 assets, right? P equal to 2. Because we hope to build a model that can explain endogenously, meaning that for a particular asset return, we use all the remaining assets in the system to explain that asset return.
Raymond, is the question between doing something trivial versus doing something interesting, or I don't understand either?
Because I'm trying to understand this is that if
I think what you're saying is obvious. The point is taken. Yeah, certainly the IBM's return can be explained in terms of IBM's return, but that would be a trivial result.
no, I understand, but so the thing is that because if this is, so I'm trying to understand the motivation. Is it
But
driven
just to kind of follow up from you, because you asked a lot of questions. So it's not just a statistical exercise, right? So there's
Okay.
a thought experiment that
Okay.
later leads to a statistical technique that turns out to work, right? But the
Okay.
initial motivation is one that just says, can we do something without factors? And something
Okay.
that's not trivial. Trivial being explaining IBM in terms of IBM, and factors being, we all know what they are.
So one way you might think about it is that going back to the original CAPM, the market turns out to be relevant, and CAPM's explanatory power depends on all assets covarying together. And so if you want to capture a independent explanatory quantity, you want to look at the covariance of the assets together. Now, if you include the individual covariance of assets with themselves, you're going to drown out that intra-asset covariance. So at least it makes sense to me that you'd want to omit the individual asset returns as explanatory of themselves, because you're trying to construct the relationship between the assets as a driving force and idiosyncratic, residual variance, and you want to separate those two.
Yeah, I think the use of the word endogenous is a little bit what could be causing some confusion. I mean, it's hard to know what that means, and it means different for different people. In here, we don't mean endogenous, meaning something belonging to the asset itself. Endogenous meaning something that's constrained to what we actually see in the market, and that's just the assets. So endogenous meaning what, can we explain a particular stock in terms of the other things in the market, namely the other stocks. But the terminology may be confusing.
Yeah, so here endogenous here means that we use the asset return within the financial market to explain as the predictors, rather than finding out any exogenously given factors. Okay.
Can I ask this question in a slightly different way? Maybe this will help. So let's just pretend the CAPM is true, okay? And we define the market portfolio as just the S&P 500 index, right? And suppose that you are only working with these 500 companies. If you if I just, instead of your framework, and I take, say, IBM and regress it onto the S&P 500 portfolio, excluding IBM, is that performance similar or worse than what you're proposing?
That's what we will see in the empirical section. And
it's a bit of a trick question also, because you just said CAPM is true. So if it's true, then obviously not, right? So
well, yeah, okay,
the answer is baked into the question.
Okay, yeah.
Also, you mean time series regression, right? You're just talking. You're talking about a time series regression, Raymond?
No, I'm just trying to mimic what they're proposing, because they're saying is that, okay, if I take one asset and then exclude that asset and then regress onto every other asset, that seems just like, if I take a S&P 500, take one of its components and regress onto the other 500, excluding that one, so 499.
But I think now you're talking about a specific technique of doing something also, which I'm not sure was present in the other discussion.
No, because I'm just trying to, like, I'm just trying to understand, is there a need to introduce this model when a similar alternative is available? But then the presenter said there's empirical evidence, so I'll wait for that.
Well, I mean, the CAPM is a one-factor model based on time series regression with prescribed returns. I don't see that much similarity besides maybe some motivation.
Okay.
Well, also there's a lot of, I mean, if I have put information, well, I'm not sure that time series regression is a part of the CAPM, but if I put information into a model about the market, it's very different from putting information into the model about all the individual stocks that compose the market. It's two different information sets.
Okay.
And in addition, the sparseness condition would not be satisfied, I think, if we used Raymond's suggested alternative. I think we're sort of in a place where we don't see the motivation for doing this, but obviously if it works, then it's interesting. So maybe we should move forward and see to what extent it works.
Okay, thanks for the discussion. Let's move on to the next part. So we proposed the graphical representation model for the asset return Y, which is AY plus E, where A here is defined as I minus D omega proposed by the theorem, but D is the inverse of diagonal of omega. And we assume matrix A here is a sparse matrix. And we make such assumption because of the following reasons. Number one, we posit that much of the variance we see in the equity markets may be explained by endogenous by the sparsely interacting issuers. Not when we explain one particular asset return, we don't need all the remaining asset return, but we only a few of them. And second, we raise the possibility that because matrix A is expressed in terms of the omega and the precision matrix, and precision matrix is encoding the partial correlation. So we raise the possibility that the partial correlations of the asset returns may be sparse. And finally, such a sparsity assumption have some implications for the model estimations. So sparsity generally achieved by L1 regularizations, and such a regularization may stabilize the estimation of the model parameters. So we can see the difference between the GRA model and the equity factor models. In the equity factor models, it is generally assumed that the factor X is uncorrelated with the residue Z. Then the covariance matrix and the precision matrix of asset returns Y given by the factor models can be provided in the equation 7. And we notice that in the equation 7, the precision matrix omega is the sum of the delta inverse plus a low rank matrix L. And the matrix L has a rank equal to the number of factors included in the model, and it is a dense matrix. So accordingly, the omega matrix given by a factor model must be a dense matrix. So from this point of view, the graphical representation model and the factor models are two different types of models. And when we compare the model structure, we can see that for the factor model, this blue represents Y equal to the factor loadings times the K number of factors plus some residues. But for the GRA model, we use a sparse matrix A having 0 as a diagonal as the interaction term times Y itself plus some residues. So the structure of the models are different. And besides that, graphical models and factor models have different decomposition for the covariance matrix sigma. And they have different assumptions for the correlations. In graphical model, we assume that Z is uncorrelated with each of the predictor in Y, but in the factor models, we assume that Z is uncorrelated with each of the factors. So for the graphical model, we assume the matrix A is sparse. This is the sparse related regularizations. On the other hand, we can see that the factor model, we assume that the matrix B is low rank, meaning that the number of factors is much less than the number of assets we have in the model. So we can interpret this kind of low rank as a different type of regularizations, right? Both models use regularizations, but they use different type of regularizations. And for the graphical representation model, it performs the minimization problem as we see in the theorem. And it finds out the minimizer over all P by P matrix A having 0 on the diagonal and it's sparse. But for the factor model, in particular PCA factor model, it performs a minimization problem given by this, where B here is a low rank matrix having the shape P by K, where K is much less than the number of assets included. And all the columns in B are also normal.
So when you say that the first minimization is done over sparse matrices A, are you assuming there's some kind of sparseness inducing penalty in the minimization?
Yes.
Okay, so you're actually not minimizing what you've written. You're minimizing that plus a penalty function that induces the sparseness. Yes?
Right.
So penalty equals a constraint, so it's a bit of a moot point. Any penalty can be written as a constraint, which is what's in the line below the minimization.
Now, I'm sorry, the 0 on the diagonal is an equality constraint, but sparseness is typically represented by the inclusion of a penalty term for non-zero entries.
Which is equivalent to putting a bound on the L1 norm.
Okay.
Right? You see it most often with a penalty. That doesn't mean that that's the only way to write it, right? An alternative way to write it is to put a bound on the L1 norm.
Yeah, thank you. That answers the question.
Yeah. So I think this is highly related to how we estimate the matrix A in our model. So in the graphical representation models, we say that A is sparse and having 0 on the diagonals, and the sparsity is actually achieved by applying the L1 penalty on the matrix A. And to estimate a sparse A, because A is expressed in terms of omega, so a sparse A means that we need to estimate a sparse precision matrix omega. So we compute the estimation for A coming from the computed estimation from omega. And this is how it relates to the graphical models. So to estimate the sparse matrix A is equivalent to estimate the sparse matrix omega. And in the current literature, there are several graphical models exist in the current literature. So here we show 2 of them. One is called the graphical lasso or G lasso, whose optimization problem is given by these equations. And the second one is called Concord. So we notice that both optimization problems having an L1 penalty at the end. So this is how we introduce sparsity on the estimation of omega. And there's a scalar called lambda that controls the level of sparsity on the optimizers. So generally the larger the value of lambda, the higher level of sparsity we can obtain from the estimations. And in the actual implementation, we don't have to manually solve the optimization problems. There are R package or Python package available online to help us to solve the G-lasso or Concord. The only input we need to get a omega hat is we need to estimate the sample covariance matrix S. Okay. So once we obtain an estimate for omega, we plug into the expression of A and we can get an estimate for the matrix A. And that is how we estimate the parameter in the GRN model. Any questions for this part for the model estimation?
Just a quick question regarding Glasso versus Concord. Which one did you end up using, and what do you think about their performances relative to each other?
Yeah, that's a good question. So, so graphical lasso actually comes from the maximum likelihood function of multivariate Gaussian distributions. So this is the this optimization problem actually coming from that. And generally, it assumes that the underlying data is following the multivariate Gaussian distributions. On the other hand, the Concord optimization problem does not have such an assumption. So Concord method can be applied to non-Gaussian problems. And generally, when users use both methods, they generally use the cross-validation procedures to find out the hyperparameter value for lambda. And on the same data set and the same procedures for cross-validation, generally Concord will produce a little bit higher, like more sparse estimate compared to the graphical lasso.
Thank you.
That's a major difference. Does that answer your question?
Yeah, I use Glasso heavily and I like it a lot. This is the first time I hear about Concord. There's a nice paper by Goto, Shingo Goto, who compares Glasso to other, probably you're familiar with the paper already, to other Leduc and Wolf type of approaches. And I find also that Glasso performs very well. Just one question, but I never heard Concord before. That R package or the MATLAB package for Glasso, is it also available for Concord, do you know?
So far, we have both R and Python package for graphical lasso. For the Python, I think it's in the scikit-learn. But for the Concord, we have the R package, and right now, the Python package is still in the development phase.
Thank you. One last question about this lambda parameter regularization for the covariance. How did you choose that? Did you just estimate it some way, or you had a rule of thumb to pick that?
You mean how to estimate the lambda?
Yeah, regularization parameter.
Yeah, so lambda here is a hyperparameter in the model, and a general method is to use the cross validation to prevent the overfitting.
Thank you.
Yeah, thanks for asking. Okay, so this is how we estimate the model's parameters. And finally, in the last section, let's look at some of sorry, I hope I was not on mute. So in the empirical study, we are interested in testing some hypotheses regarding the properties of the graphical representation model. We're interested in checking if those hypotheses is empirically true for the hazard return for the United States equity returns. And the first hypothesis we'd like to check is whether an estimated graphical representation model can explain the out-of-sample variance in the US equity returns, at least as much as a factor models. So to conduct such a hypothesis, we focus on the S&P 500 index component stocks, and we download the historical returns of all the S&P constituents. We pick up 2 time horizons. One is the first half of the year 2008, which we call the financial crisis period. And another one is the first half of the year 2018, which we call the economic expansion period. So for each period, we split the historical asset returns into the in-sample part and the out-of-sample part. And in the in-sample part, we use the data to feed the model. So in particular, in the factor model, we consider including 3 factors. And in the GRM model, we use the cross-validation to determine the hyperparameter and compute the estimated matrix A. And for the out-of-sample data, we use the data to measure the model's performance. And the performance is measured by the root mean squared error defined here.
Sorry, is this daily data? I apologize if you said that and I missed it.
Yep. Yeah, it's daily data. So here daily means that for each trading day, not including the weekends or holidays.
I got another question. Where does that 3 come from? Is that optimized or just typical?
So 3 here, we determine 3 because in the empirical study, we also compare the Pharma-French model. And the Pharma-French model generally has 3 factors. So to make the fair comparison.
Got it.
Yeah. So here we can see that we compute the R mean squared error for each type of model For the factor model, we compare the Farmer Friends three-factor model, PCA three-factor models, and for the GRM model, we consider using the graphical lasso or the Concord. So we can see that GRM model has the RMSE a little bit smaller than those RMSE coming from the factor models. So the residuals of GRM models are slightly smaller than the factor models, and this explains that the GRM models can explain the out-of-sample variance for the accurate returns at least as much as the factor model. The second hypothesis we are interested in.
I'm sorry, can you go back to that for a second?
Yeah.
Previous slide, please. So what are the numbers in the table? This is the residual, or?
This is the residuals, and the magnitude is multiplied by 10 to the power minus 4, I think. It's very small.
So saying that a different way, the R-squareds are higher for Glasso and Concord in your method, is that right?
Right.
Yeah, okay. Okay, thank you.
Yeah.
Yeah, pretty much the smaller the RMSE, the better the out-of-sample performance of a model. So second hypothesis, we would like to test whether an estimated graphical representation model will exhibit a large degree of sparsity in the interactions among US equity issuers. And such a sparsity can provide interpretability for investment practice. So to test this hypothesis, we still use the historical returns of the S&P 500 component stocks, and we focus on the time period from the economic expansion only. And specifically, we choose the graphical lasso as the graphical model. And we test the hypothesis by two ways. One is that we visualize the matrix A hat. Another way is that we conduct a community detection for equities for all the component stocks based on the sparsity pattern of A hat. So here is a visualization of the sparsity pattern of A hat. Here in the slide, we can see that under our chosen data set, A hat is a 500 by 500 matrix, and it is a matrix with very high level of sparsity. There are about 95% of the elements that are zero. For the 5% non-zero elements, we use the blue to represent the positive partial correlation, and we use the red to represent the negative partial correlations. So we can see that the blue pretty much dominate the color in this matrix. Right? So that means
I'm sorry, isn't the sparsity driven in part by the choice of hyperparameter?
Yes, exactly.
So if you find that it's really very sparse, that's just a statement about the hyperparameter you used.
Yeah.
Now, I guess you said you chose it by cross-validation.
Yeah.
So it was determined statistically, but can you say a little bit about what that did? Because the choice of the hyperparameter lambda is equivalent to the amount of sparsity with which you'll end up. It encodes the same information.
Well, I'm not sure it is right to say that it's not determined statistically, but
no, I said it was determined statistically through the cross-validation procedure.
Yeah, yeah. The cross-validation procedure actually is a data-driven procedure, right? So lambda, which value is the optimal value for lambda, is totally driven by the data, by the historical asset returns we observe from the market. So this sparsity pattern is not determined by myself. It is determined by the data, by the market. This is the market that tells us this is the optimal level of sparsity that we can use in the model.
So you may do this in a slide, in the next slides, but it would be provocative, at least, if it turned out that non-zero entries corresponded to something like industry sectors.
Mm-hmm. Right. Yeah. So based on the sparsity, we are able to plot a graph. we are able to plot a sparse graph based on the sparsity pattern of A hat. And we can see that in this graph, each vertex represents a security, an equity. And if the two securities have positive partial correlation, then we plot a blue edge connecting the two vertices. Otherwise, if the two securities have negative partial correlations, then a red edge is plotted to connect.
Do we know what the securities are? Like, are the red ones utilities?
Yeah, so here in this graph, we have 500 vertices. It will be quite messy to denote the names, label each of the vertex.
Yeah, but you could know if the red ones were utilities. I mean, you can still know qualitative things about, I mean, those red lines are rare. And I'm wondering if there's something that you can say about which securities have the negative partial correlations with others. I mean, I don't know.
Yeah.
By sector, by size, by some familiar characteristic?
Yeah, that's a good question. So that's what I'm going to talk about next, because right now we have too many vertices because there are so many stocks in the S&P 500 index. So we are wondering if we can extract some information, group information from this from this graph, right? So that's how we conduct the community detections. So here we conduct the community detections, and we detect 11 communities solely based on the sparsity patterns of the matrix A hat. We plot the subgraph for each community. Each vertex here is labeled with the equity symbols, and all the vertex names is called based on the industry sectors they are belonging to.
So there are the sectors. Great. As we discussed a moment ago, can you say a little bit about the actual algorithm for community detection?
Yeah, so here the details of the algorithms for the community detection is not the focus of our work, but here I can talk a little bit about it. So there are a variety of methods for the community detections, and we conduct the community detections using one of them. We are using the random walk method. This method tries to find the densely connected subgraph by detecting the short random walks in a graph. And we implement this method by using the R package called iGraph. So this is the data-driven way to determine the communities.
Thank you very much.
Yeah.
So when I look at the names here, both within financials and consumer staples, there are some that I recognize, but a lot that I don't, suggesting that they're relatively small companies. Is that correct? So
yeah.
On the financials, BAC is Bank of America, so I recognize that one, and there's presumably Schwab, but there are not so many that I recognize. So is that right? That there are a lot of relatively small financials
right
in here?
Right. So we have BAC as Bank of America, and we have JPM as JP Morgan, and we have the PNC Bank, right, and USB. These are the famous banks, financial institutions. Besides that, we also have some national and small banks and financial service institutions here.
You also have the CME and ICE. That's interesting because those are not traditional financials.
But as we can see that here, this community is dominated by all the financials coming from the financial sectors. And on the right-hand side, this community is dominated by the consumer staples. And here we have more communities. So on the left, this is a community dominated by the utilities. And the other one is dominated by the real estate companies. So for this community, we can see that there are a few companies from other sectors. So for example, one is the AWK here. AWK is, the full name is American Water Works Company. It is a water utility company. So I think it should be not surprising that this company is connected with some real estate companies, because water utility is highly related to real estate industry as well. And here are additional communities. The left one is kind of a mix of different sectors, but we can see that half of the companies comes from the consumer discretionary sector. Consumer discretionary companies deliver goods and services that are connected as non-essential by consumers, but desirable if consumers available income is sufficient to purchase them. So consumer discretionary sector may have a wide connection with other sectors. So it should not be surprising that this community involves many other sectors. And on the right-hand side, this community is dominated by information technology companies. And the companies from other sectors also get involved, as we can see. But if we take a closer look at these companies, we can find out that many of these companies, not in the information technology, have business highly related to information technologies, right? So for example, here we have Google, right? G-O-O-G, Google. We have the Facebook, and we have the EA here, which is the Electronic Arts. So despite they are classified as communication services, they are definitely highly related to information technology.
Okay.
And
What's the date? Sorry for interruption. What's the date of this analysis?
What is what? Sorry.
The date. When? What?
The date is,
yeah. Please remind me what the date is.
Yeah. Sorry. The date is shown here. From
because there was a GICS reclassification in 2018 involving IT and communication services. So they just kind of, some committee went in and changed some labels, and it sounds like it's close to your date. So it's just a good thing to be aware of with that particular graph.
Yeah.
I'd also think one of the more interesting investigations would be when you have a given sector which is represented in multiple communities. For example, consumer discretionary is in 3 and 4. I think healthcare may have been in 2 as well as 4, and of course it's in 3, to understand the companies within that sector that are in different communities and see if something jumps out as a reason why, in one case you have an HMO, in the other case you have a pharmaceutical. That would be very interesting. They're both in healthcare on some level. Medical equipment is different as well. If that were the case, it would underscore the power of this analysis to identify connections going beyond what existing methods have been able to achieve.
Mm-hmm. Yeah, right. So, so in addition to the Google, the Facebook, we also can see that we have the MSCI, we have Amazon, we have the banking bookings holdings. These are the internet and direct marketing retail companies, right? They are highly related to information technologies, despite they are classified as consumer discretionaries. And we have MSCI, we have S&P Global. These are companies offering financial exchange data, data services, and they are classified as financial sectors, but definitely they are highly correlated with the information technologies. So as we can see, we find out these communities not rely on any other information. We only rely on the sparsity patterns of matrix A hat. So it is really a fascinating way to conduct a community detections, to discover the actual connections among the asset returns, to discover the real interactions among the companies. And such a community detection is purely based on the sparsity patterns of the graphical representation model. It's purely data-driven. It is purely data-driven, right? So it provides a very interesting interpretation for the asset dependencies for the investment practice and for analysis purposes. And such an interpretation is, I think, is more interesting, more applicable than the sector classification. And this is something that we cannot do with factor model.
So I just want to throw something in here that you may or may not be aware of. When BARA builds its covariance matrix, it uses partial sector and industry classification. For example, an automotive company like GM would be, say, 80% in auto. We think of as an automotive company like GM would be 80% in automotive and maybe 20% in financial services. And they do this with fundamental data based on their revenue breakdown, or I'm not exactly sure what, but some fundamental data they use. And a company can be in as many as 5 different industries, I think. And then they take that classification and actually use it in the building of their fundamental factor model to forecast correlation. So a question to you, if we could get hold of this data, is do your kind of community detection picking up the same things that their fundamental analysis is picking up? And also, are your risk forecasts more accurate than theirs, which uses the same kind of idea?
Yeah, I think it would be also useful, picking up on Lisa's comment, if you could, having identified the communities, then come up with an appropriate measure of association for individual nodes, individual stocks with each community. And you could see, for example, that General Motors was primarily in industrial, but also in finance because of GMAC. And that would also reinforce the efficacy of this method as an alternative. That's, of course, so appealing precisely because it eliminates explicit human judgment.
Yeah, I think so. And I would like to comment on this. So this community detection is pretty data-driven because for a particular asset for particular companies, how to classify its business is kind of not that easy. Like for example, for Amazon, this is appropriate to classify to consumer discretionary or information technology. It is hard to tell, right? So here we leave this question to the data. We ask the data to decide how to classify each of the company, how to decide what is the most appropriate communities defined for each of the companies.
Excuse me, I have a question. How much do the community change in time? So if you were to run the same analysis, different chunk of time, would the community stay roughly the same?
We haven't done that work, but I guess that as time evolves, pretty much we will see some changes in the communities. But I think the main structure probably.
That would be quite interesting to check, right? Because you will want some sort of stability in the community detection process.
Yeah, but that's something we can do, but we didn't do that. But yeah, that's something that is interesting to do. Right now, I do not have a deterministic answer for that. Okay, so the last hypothesis we would like to test is about the out-of-sample variance. We are wondering, since GRM model only relies on a graph to explain all the asset returns, we are wondering if we add additional factors to the GRM model, can the GRM model perform better? So to test that, we test if the following model will deliver the better out-of-sample performance, which is y equal to rho ay plus bx plus z, pretty much similar to the spatial interaction model, but here we use the A estimate from the GRM model. So to test that, we consider introducing the pharma fringe 3-factor models, and A is defined in the GRM, and rho is a scalar to be estimated together with B using either least square or the maximum likelihood. And for the data, we focus on the historical return of S&P 500 component stocks. So here is the result. Those numbers are RMSE. So we can see that for the proposed model, their RMSE do not significantly smaller than the RMSE coming from a GRM model, meaning that once we have the matrix A, adding additional factor B in the model does not help at all. We cannot obtain any additional benefit by adding additional factors. So that means that the graphical representation model is sufficient to explain the out-of-sample variance of equity returns. Once we have the GRM model, we don't need to add any additional factors. Adding additional factor does not increase in the explained variance for the equity returns. Okay, so GRM model is sufficient. Okay, so I think that concludes my talk today, and thank you all for attending and for discussing these materials. And so sorry for running out of time. So for the next couple of minutes, do you have any questions?
Yes, it would be interesting to see the evolution of the estimated A matrix over time. To the extent the communities estimate proxies for true sectors or other groups, you wouldn't expect them to be completely stable, but you'd like to see some stability, and you would like to understand the changes over time.
Yeah, I think this is a good proposal, but I think one issue we need to solve is that when we compute the matrix A across time, how can we quantify stability? Because matrix A is a P by P matrix, right? How can we quantify the stability of a graph? That's something that we need to work on first before we check the evolution, right?
I think the stability of the communities would be one obvious measure.
Yeah, so for the community, so here community, so let's say for one period we have community 6, right? And later on it changed to community 7. How can we say that it comes from the same community? This is an unsupervised machine learning question, right?
But you can check each firm, the interaction that each firm has with all the other firm, and see if those interactions change on average. So you don't care about the label of the community, but you only care about whether a firm always interacts with the same other set of firms.
For each firm, okay. Yeah, we can consider doing that.
So I've got a couple of suggestions. So one is that you look at 2 periods, each which has a 3-month training period and then a 3-month out of sample period. To be convincing, you need to do that for a broader range of times. In fact, I don't see why you couldn't effectively do this for, let's say, a 20-year history, and then you'd be more convincing that the method seems to do somewhat better than alternatives. Second comment is one of the reasons one would like to use either the MSCI factors or the Fama-French factors or latent factors is to predict risk of portfolios. And I've been thinking about, can you do it with this? And I'm not seeing how, but that would be something, maybe you do know how, or if not, that would be something that would be very useful to work out how you can use this to make risk predictions at, say, a 1-day horizon.
Thank you, Robert, for the questions. Regarding your first question, I think the reason we did not use all the time horizon is because the financial market evolves all the time, and it changed. The financial market itself is not stationary. Like, for example, for this year, definitely it's not a good idea to use the entire years of observation as an estimate.
That's not what I was suggesting. I was suggesting to take rolling windows. So go back the last 20 years or 30 years and then have a rolling window, 3-month training period, 3-month prediction period, and then roll it forward either 3 months or roll it forward 1 day at a time. And then, look at that. So I mean,
what do we look at specifically?
Well, you could look at whether the residuals are smaller in almost all of those rolling windows, all of them, half of them, or are they only smaller in these specific 2 windows you picked?
Well, but we have a plot from 2000, 2018, right? That's roughly what you're, I mean, so the main plot is really at the beginning, not at the end.
This is,
Aaron, do you want to go back to
so
that?
which plot is that?
Yeah, we should have actually put it at the end. I mean, the most important, this one is what I would consider the most important plot, which says that a sparse precision matrix can explain more variance out of sample than a PCA model over a span of 18 years.
And this is a rolling window.
Yeah,
In the rolling window, right?
3 months, is that right, Aaron?
Right.
And
Okay.
so, yeah. And so there's a lot of related statistics to this that we're not showing, but sort of the,
right.
You know, at least one of the major hypotheses here was that we don't want to deal with factors. We want to explain, we want to ask the question of whether variance can just be explained in terms of other assets. And this necessarily leads to assuming, you know, sparse interaction, you know, from the statistical perspective, but perhaps also from just the modeling perspective. And it seemed to me, at least when I saw this, I was very surprised. I thought, that, you know, there's no way that a sparse precision matrix would be able to explain this much variance, but sort of this is kind of the more surprising of all the findings.
Yeah, so I agree with that. And I think this is maybe more compelling than picking the 2 specific time periods.
Yeah.
But the second part of it is, so I give you a portfolio and I ask you, what's my value at risk one day? Can you do that out of this?
Well, we have an estimate of a covariance matrix, right? So in the end, it still comes out to what can you do with an estimate of a covariance matrix, right? We can't do pricing in the sense that we don't have factors, which we wanted to get rid of anyway, on, you know, based on the fact that you know, I don't really know what they are, right? The whole allusion to invisible hand is sort of like, well, what is it as a scientific theory, right? What is a factor, right? It's kind of like in physics, you don't have gravity factors. Nobody does regression to find out how much the moon, you know, affects the Earth, right? You have an explanatory theory, and the one we're building here is in terms of how much variation can you explain endogenously, and then maybe the rest sort of is up to kind of question.
Why not, Alex and Zhipu, why not forecast portfolio risk with the covariance matrix? It's easy.
Yeah, that's what we, yeah, I think that's the answer, right? Anything, you know, we have an estimate of it, and so anything that one can do with a factor model estimated covariance matrix, you can do here.
So you could make bias statistics, which is what they do at Barra. And I mean, for better or for worse. I mean, there's one thing that we observe is an optimization bias. So if you take that covariance matrix and use it to build an estimated portfolio, that forecast used, you will under forecast risk for that portfolio, right? Something we know.
Yep.
And a question is, does this lower an optimization bias in any way?
That's actually another portion of Aaron's thesis, which he's not showing, but
oh, good.
Yeah, he can maybe talk a little bit about some of those results, but yeah.
I think it has to be another time, though. We are totally out of time, and I want to respect everyone's calendar. So let's thank our speaker for a really beautiful talk, and thank you, audience, for great questions. I want to mention that next week, Tuesday is election day. We will not be having a seminar Tuesday, so please go out and vote if you have not already. We will be back in 2 weeks. CEDAR postdoc Ting Wang Gan will be presenting, and between now and then, stay safe out there, everybody. Great to see you all.
Yeah, thank you, everyone.
Thank you.
Bye-bye.
Thank you.